Ever wondered how your smartwatch can analyze your heart rate in real time without draining your battery? Or how a voice assistant on your phone understands commands without needing a constant internet connection? The answer lies in a revolutionary approach to AI, structured state-space models, SSMs. These aren't just another neural network. They're a paradigm shift in how we design intelligence for power-constrained devices. Let's unravel how they work and why they're set to redefine edge computing. Traditional AI models like transformers excel at tasks requiring pattern recognition, but they have a critical flaw: they're memory-hungry. Transformers process data by maintaining an attention mechanism that dynamically weighs every previous input. For a 10,000-word document, that means 10,000 attention weights, each requiring storage and computation. This quadratic complexity makes them impractical for devices with limited power and memory, like wearables or IoT sensors. Enter structured state-space models. Unlike transformers, SSMs represent data through a state vector, a compact mathematical summary of the input stream. Think of it as a neural network's version of a checksum. Instead of storing every detail, it captures the essence. For example, if you're tracking a heartbeat, the state vector might encode the average interval between beats, not every individual pulse. This reduces memory usage from N2 to O1, making SSMs orders of magnitude more efficient. But even SSMs need optimization to run on real hardware. That's where Quantization-Aware Training, QAT, steps in. QAT isn't just about shrinking models, it's about teaching them to think in lower precision. Traditional AI uses 32-bit floating-point numbers, but QAT trains models to operate with 8-bit or even 4-bit integers. This isn't just compression, it's a fundamental shift in how computations are represented. Here's the technical kicker: QAT simulates hardware constraints during training. Imagine training a robot to walk on uneven ground. By the end, it's adapted to real-world instability. Similarly, QAT exposes models to quantization noise, rounding errors, and hardware-specific quirks, ensuring they remain accurate even when deployed on low-precision chips. The result? Models that are both compact and robust. Researchers tested this approach by deploying quantized SSMs on memristive crossbar arrays, analog hardware that performs computations directly in memory. These arrays eliminate the von Neumann bottleneck by storing weights in physical resistant states, enabling ultra-low power operations. However, they're prone to noise and non-ideal behavior. The results? Computational demand dropped by 90%, while audio recognition accuracy stayed within 0.5% of full-precision models. Energy consumption: a mere 16 milliwatts compared to a GPU's 10 watts, a 625x improvement in energy efficiency. For context, this could extend a smartwatch's battery life from days to weeks, or enable real-time AI on solar-powered sensors. This isn't just academic. Imagine a wearable that continuously monitors your blood oxygen levels without requiring a constant Bluetooth connection. Or a self-driving car's sensor fusion module that processes LiDAR data in real time using a fraction of the power. SSMs with QAT could make these scenarios viable, bridging the gap between cloud-scale AI and edge devices. So what's next? As memristive hardware matures and QAT techniques evolve, we're looking at a future where AI isn't just powerful, it's ubiquitous. From medical implants that detect seizures before they happen to satellites analyzing climate data on the fly, this research is laying the groundwork for a world where intelligence is as accessible as electricity. The next time you glance at your smartwatch, remember, it's not just a device. It's a gateway to the future of AI.